In computational linear algebra. This lecture will be looking at linear dynamic models and Kalman filtering. None of this material is in our book, so you'll have to watch the video with respect to what you're expected to do in this. Make sure you understand the terminology. There's a lot of it. You don't have to know all the Gaussian distributional stuff, but you do know how to build basic linear models and what Kalman filtering is all about. So let's start with a motivation that some of you will find compelling. Animation, big area in computer graphics area, is maturing, but it's still pretty hard to create. And underlying these models is a lot of work we have to do to build computational models to make these things meaningful and faster today. So, originally animation was done by having keyframes where artists would draw individual frames over time, and then you would put them together to make the movie sequence out of them by putting these together. We think of keyframes in terms of physical objects. We can think of a ball in one position, a ball in a second position, a ball in a third position. And what we really want to do is build a nice, smooth trajectory that it interpolates between them. And that's the beginning of what we want to do with sort of animation stuff, is be able to control this. Now, with just a ball, it's pretty straightforward. We'd like to be able to make that ball move smoothly. So how do we do that? Well, we use this idea of dynamical models. So we can think of particles. Going back to basic physics, we can think of for a simple one-dimensional particle, we have, for example, for that ball, we have some initial velocity. It's vector u. We're affected by gravity, mass times gravity. We can move in the x direction, and then we have our y height, and we can write a basic physics model that says x dot, its velocity in x is equal to ax plus b times u, and fill in various quantities depending on what our model is supposed to do. If we want to stick in some rigid body dynamics, that is, we linearize this equation around u equals 90, we assume there is no change in velocity, then we can put this back in that model. So this is the idea, and of course this is a very simplistic model. What we really want to do is generalize this. Now, how's this related to where we've been this semester? Well, we've been looking at linear algebraic systems where we have a system of equations ax equals y, where we have our matrix A, our vectors x and y. And the model we just looked at, this linear dynamical system, you'll look at and you'll see it's actually quite similar. We have a bunch of coefficients times a bunch of elements that say whether or not we're looking at x dot, x double dot, for each of the various variables. And then the equations of motions become something like some coefficient times the acceleration plus some coefficient times the velocity equals some constant. That's a linear dynamic system. Clearly you can see linear dynamic systems and linear systems are just a special case where we've constrained is that the variables on the right-hand side, the coefficients we're solving for, are related to physics of motion. Now, for the ball, it was pretty simple. When we get to complicated characters, these kinds of motion equations can become pretty sophisticated. Complex characters like Woody have 200 facial control variables and 700 overall controls in his body. And as the computers go to generate these things, they have to be able to control these physics systems that make them interact as they move and relate all these variables. Now, not all of this is done by just inputting it by hand. In fact, a lot of what we want to do for a lot of animation stuff is driven by this idea of motion capture, or MoCo for short, where actors use specialized suits, and more we're moving to less specialized suits, that track the body positions with the features then allowing it to solve it. MoCo is not a complete panacea. You get a bunch of features, but you still have to map them because the actual motion capture may not be the actual 3D shape of the object being done. So if we want to animate Gollum or have Tom Hanks' face control this, we have to map those two between them. So we have to understand how to parameterize them and map them and then interpolate them. So we can think of our generalized body having a bunch of positions and parameters. So we can think of every joint in an avatar, give it some 6 degrees of freedom for each of those. With all the joint angles, you end up with 35 different parameters to represent just a basic silhouette type shape. in things like the Kinect, they're actually using this kind of model to represent and reason about what is your body shape. When you think about forward kinematics, given a shape, we can map it to where everything will be. And in inverse kinematics, we take a bunch of observed positions and try and figure out what is the body shape. So inside the Kinect, it's continually trying to use the camera information to take the observed positions and estimate what is the body position, which you can go about this. So this idea of sort of human model target interaction, we can ask questions like what motions are likely and how we can put those together. And there's really two parts to this. Computer animation is how we drive from models to generate graphics. Computer vision, which is my field, is how we take things we observe in the field and build the models. So a simple form of this might be tracking a displayer to dispatch spots. Right? You want to predict where things are going to go in the future, so your game might interact with them. So it doesn't even have to be computer animation. Regular gameplay has this. Predicting future trends for travel, prices, all of those things turn out to be in the same general category. Not all of them will, however, be linear. So why do we want to look at prediction and tracking? Well, for motion capture, recognition of motion, things like video surveillance use this technology. Targeting within the military, or if I want to send out an interceptor, my missile has to guess where their missile is going to go so we can intercept it. All of these. You could probably think of lots of other applications. Some of them are even things you might not think of as physical, so predicting scores within a game, predicting life health points, interacting with bots inside of a game, all of those can also be done this. So part of what we want to look at now for the rest of this lecture is how are we going to do this? What kinds of models can we do to predict this, to deal with this sort of motion information? So the first thing we want to recognize is the actual state of the object. The joint angles and whatever are not things we can really measure. They're going to be hidden from us. Those are our parameters of interest. What we really want to do is try and figure out what's the physics based on what we see. So let's think of a simpler example to begin with. Imagine that we see a ball, right, and we're trying to estimate its position and spin and everything else. Well, from a couple of observations, if we have a model of what that ball looks like, we can take those state variables and say, okay, if it went from here to here to here, then it's moving on this physics trajectory, and we can put that together. And they, of course, don't have to be just simple physical objects. When you think of a state variable, for example, if I want to actually know something about this object, the state variable might be the height of the water, but if I'm looking from the side here, I can't see the water, but I can see how this piece moves up and down, and therefore from it I can infer something about the changes in the height of the water. So measurements are we get to directly observe the center of the ball, the height of this object, but not the actual internals, the spin of the ball we can't see, the height of the wave we can't see. So given what we can see, say the MoCo capture points, we can ask what is measured, what do we infer, what model do we put them together. And then given that, one of the things we're going to want to deal with is how we put them together. So if we measure, for example, position, which is pretty easy for us to see, we can ask about what we can infer and then what model do we need to do that. So let's say we can see position. So I see a bunch of positions. Then if we can estimate velocity, we can predict a future position. Okay? And so that becomes our very first idea of how we're going to do this. We're going to get some initial position. We're going to estimate some position for where that might be. We'll get some new measurement. In the next frame, we're going to get it. Then we're going to update our model of what's going on. Now, if all we do is predict our last measurement, that's not going to be very interesting. So we want to actually view this as inferring about more sophisticated models. Our hidden state is going to consist of the true parameters we care about, for example, position and velocity. Well, we can't measure velocity, we can measure position. And our measurements are going to be noisy observations that result from the underlying data. We're going to know that as y. And our problem then comes, given we've seen a change in time from x sub t minus 1 to x sub t, we get some new observation y. So given that, we then want to update our state. So our goal is to recover the most likely state of xt. So now you can imagine if all we're doing is looking at position and our state is position and velocity, given two changes in position, we can use that to estimate velocity as just the change in position divided by the time between them. That gives us an estimated velocity. So you already have some very basic ideas. The question is, what's the most likely? we want to use all the observations seen so far, not just the last time frame. And we're going to want to actually try and think about noise and representation of that. And we're going to choose some upfront some knowledge about the dynamics of the state transition. For example, do we assume the point is moving with constant velocity, or maybe it's constant acceleration, so velocity can change, or it's constant jerk and acceleration can change. We need to understand where those are going to be. So our first question is to represent the dynamics that govern the changes in state. Then we have to look at how the relationship between states and measurements plus uncertainty, so how are we going to measure the noise. We have to have some compute cycle for how to do our updates. We'll put those all together. So for this, we're going to consider the representation of a class of linear dynamic models with associated Gaussian noise. These are by far the most common Gaussian probability distribution functions. Don't worry if you don't understand probabilities for this class. You don't really have to understand where they come from, but I will use them as part of the motivation so that those who know them can see these things in context, and for those of you who are going to take probability statistics later, you'll see when you get there how these might be related. So that's our representation, linear dynamic models with Gaussian noise, and our updates are going to be using the Kalman filter as an equation. So we're going to go through these bits and steps. So let's look at some of our intuition for tracking. So we have some measurement at time t. Okay, at a time t plus 1, we're gonna assume we see this target move, right? So the box was here, the person is now here, so their motion is moving that way. We get their new position. We can use that to update our model and put them together. So we have some belief of where they are at time t. We get some measurement, and then we're going to use that measurement to update our new model. Notice we don't just believe the new measurement because we assumed we know the measurements have noise, but we also don't just believe our last state. So our belief becomes affected by the measurement, but not exactly equal to the measurement. And that's a question of how much we trust our measurements versus our models. Okay, and that gives us a corrected prediction we can then go ahead and use. So again, digressing for those who haven't seen probability, but I want to put this in context, and you'll see how this is related to some of what we're doing in linear algebra as well. So let's say we're going to represent noise by a Gaussian PDF. It turns out we represent that by mean and covariance. Remember covariance from when we did PCA? Well, it's the same covariance concept. So we're going to represent a distribution as a Gaussian, and in multiple dimensions, we're going to have our mean and our covariance matrix, and that gives us the representation for our Gaussian distribution. We have some dimensions, and we have our determinant we get from the score bars are our determinant from the covariance matrix. And again, you don't have to worry how to compute these just underlie what we're going to do. And covariance and Gaussian noise allow us to have things that are fat and broad, things that are very sharp, things that are actually asymmetric in shape. So we can have directional noise, which makes sense, for example, where we might have much more uncertainty in, say, acceleration than I do about velocity. So we're going to want to be able to represent all of these. Again, because we're looking at covariance matrices, right, we can look at their cross sections and think of them in terms of singular values, and these become related to our covariance matrix computations. So coming back to our tracking, we're going to think of our hidden variable with noisy observations. Okay, and our noisy observations, what we really want to do is we're not going to add noise to our measurements. What we're going to do is try and estimate what's going on with the noise in our measurement. So as we step from time t minus 1 to t, we get a new observation. Our goal is now to update that most likely state given all the observations and our knowledge. And we're going to do that by viewing this as a process. So our recursive process is, assume for a second we had some initial prior on the state. In the absence of any evidence, so before we start, we assume something. And then we're going to correct that based on our first measurement. Given our corrected estimate for time t, we're going to predict the frame for time t plus 1, correct it by looking at the difference between what we predicted and measured, and then update our model. So we had some prediction. We have some model. We use that to make a prediction. We get some measurement. We measure the error between what we predicted and what we measured. correct our model, and update that. And this correction is what's going to allow us to update our noise model as we go along. So now we need to come back to, we know how to represent the dynamics that govern the changes in state in our model, how to represent the state changes plus our uncertainty in those measurements, how to compute the cycle of updates. So as I've already said, we're considering linear dynamic models, and we're going to then update them with the Kalman filter. So let's look at some example models just so you see what we mean by example models. We'll look at a point with constant velocity, but you could easily be looking at periodic motion, points moving, constant acceleration, full body dynamics. The basic concepts become pretty simple once you know the basics. So let's just say we have a 1D point in moving along a one-dimensional axis, so we have 1D position. So as it moves along, we have some speed. We can think about our state as just estimating what is its position along the x-axis. The actual measurements, these open circles, are what we measure, and you'll notice that was not a smooth motion. It was actually a little bit jerky. And at some point in time, our model is then going to estimate those new states given some initial position. So we get our measurements, we put our model together, we estimate our state. So what's that state model going to look like? Well, we're going to have a point as a position plus a velocity. So at time t minus 1, we add delta t times our currently estimated velocity, and we assume there's some noise, and that gives us some point E. Even though we write plus epsilon, that's just to remind you that the noise is there. We're not actually going to estimate it. Our velocity is we're assuming constant velocity, so we're going to assume it's the same. So again, here we have c, like epsilon. These are just things remembering that there is noise. We're assuming that our noise is Gaussian distributed with mean and covariance. So at this time, xt is equal to d r times x t minus 1 plus whatever the noise is. Well, that's just going to write this transformation matrix D as 1 delta t 0, 1. If you look back up at these equations, you can just sort of read that off. 1 times p minus 1, delta t times ve. Those are our two state variables. But v's equation doesn't have any p in it, just has v, so it's 0, 1, plus whatever our noise is. Our measurement, however, doesn't get to measure velocity. Our measurement matrix is just 1, 0 times p and v, because we're just going to project away v, giving us just that particular measurement noise. So this gives us our data representation. We have our state vector, our transition matrix, and our measurement matrix. And now if we use that, we can get a velocity. If we now want to extend that and add acceleration beyond our velocity, so it's no longer constant velocity, we expect things can actually speed up, then we need a more sophisticated state vector. Now we have the point plus its velocity plus its acceleration. Other places in the equations we might write this as x, x dot, and x double dot, using the dot notation from physics. Our position is just position plus delta t times our velocity plus some noise. Our velocity equation now is not constant velocity, it's velocity plus delta t times acceleration plus some noise, and we're assuming here constant acceleration. So we get our data transformation matrix. We have these are our three state vectors. So what do you think the first row is? What do you think the full matrix looks like? Yep, just reading it off from here, you should see 1 delta t 0, 0, 1 delta t, and 0, 0, 1. The coefficients if I write all of those equations out. Again, however, our measurement is going to be position only, which means our measurement matrix now is going to look like 1, 0, 0, because we measure p, we don't measure the other two. So now you should have a pretty good handle on where we're going to go. With that, again, from a noise modeling point, x is assumed to be normally distributed with a mean vector and a covariance vector. And our measurements are going to have just a measurement projection. Now, all this was 1D. What happens if we want to go to 2D? Well, now we need a more sophisticated state vector, but you can also see the practicality of this. If I have some pursuer and some evader, I don't want to just aim at the evader. That would be if I just use their measurement as their current position. The whole point of what we want with the Kalman filters is to be able to predict where we think they're going to go, so we cannot aim for where they were, but where they're going to be. Right? In the words of Wayne Gretzky, right? skate to where the puck's going to be, not where it is. Now we still have to worry about noise, but our model becomes a little bit more complicated, but not too much. We're going to think of our position vector x as having two positions, x and y, and in this case constant velocity x dot and y dot. If we wanted to go to acceleration, we'd have x double dot and y double dot. We'd need three of them. Our transition matrix then has x and t, y goes y and t, y dot and y double dot. So we'll see how to put this into a matrix a little bit later, but you should see this now as a 4x4 matrix that looks like, for this vector, what is it going to look like? Well, it's going to look like 1, 0, t, 0 for the first row, 0, 1, 0, t for the second row, 0, 0, 0, 0, 0, 1, 0, and so on. Okay, now in 2D, our estimates are going to be complicated, and one of the things we want to recognize is if we don't do anything, our errors will keep growing over time, because if I just keep going on a particular path and I have an error, it grows with the length of time that we estimate with. So we want to figure out how to improve our noise model over time. So in our linear dynamic model, we describe the a priori knowledge about the system dynamics, which represents how things are going to evolve with noise. So I have my state vector as Gaussian with mean d and covariance matrix. Okay, now if we think about these as matrices, right? X is a n by 1, d our transition matrix is n by n, and n our position vector. What's the covariance matrix? It's also n by n. Our measurement model, at every time step we get a noisy measurement, so that's just putting them all back in the noisy model state. Notice y is m by 1 because m is an m by n matrix. It's going to do projection. And these are all transitions in time from t minus 1 to t. And the measurement matrix is from t to t. Right? These are both at the same time because it's a projection of what I measured at time t down to my observations at time t. So now let's see about how we do these updates with our common filter. That's the set of steps. Now we're the last one, common filter. So the key idea of the common filter is that linear models interact well with Gaussian noise. They make the prior Gaussian and everything else in the calculations are very easy. They're very easy to represent these things by matrices. So for our linear measurement model, we're going to have our measurement is going to be some matrix times our current state plus another matrix, which remember there's noise hanging out there. We don't actually add the noise, but we're going to try and model what that is. And our linear change, our change in state, then our errors are going to look as, again, some linear model times our current state plus some d, which effectively is trying to handle where we're going to go with the noise. And we can fill in some simple state models. If nothing changes, then A is just the identity matrix and B is 0. C is the identity matrix and D is 0. That's assuming nothing is changing. As soon as we start adding prediction, we're going to want to change those models and update them. So the basic idea is not just to take my position and then have some estimate. So if I have a 1D variable, here I have x, here I have x dot, it's velocity. So at some point in time, I'm at some position, then I have some uncertainty about how fast the velocity might be in the next time frame. As soon as I get a measurement, two things happen. I get to update my x position, because that's what my measurement was. X was in this range. But when I update that position, because my model predicted some set of velocities, this update also lets me update my estimate of x dot. And I end up with some next prediction that says, okay, I was here, I have this as my x dot. Now I can use those if you ask me for the next delta t, I can project that ellipse forward in time with some level of uncertainty. Now, it might actually be much larger than you think. I don't just take that last thing and move it along because I, again, had a lot of uncertainty about what my change in velocity was going to look like. So depending on that change in velocity, x could be anywhere from here to here, and its velocities could be in this range. So now, the basic idea of common then is to take our time prediction. We know our predicted state. We're going to predict over to the next state using our mean and standard deviations. We receive a measurement. Now I'm going to do this correction stage where I look at the measurement. I looked at how far was my model from what I actually measured. I get some new probabilities based on that, giving me some new estimated mean and covariance. And then I use that to update my model in advanced time. So for an example, coming back to the 1D example we had, which is a 2D state vector, 1D position, we have position plus velocity. I get some measurement. Coming back to this example, as they move, I can estimate their position, get a new state variable, and even though the measurements might be quite noisy, and they're noisy because in this kind of example, as a person's walking, estimating where they are in the image is not as trivial as it sounds. So we'll get their measurements going back and forth, but this will give me a state vector that shows them moving pretty consistently forward. So in applying the Kalman filter, we get the state. We get that's going to be our overall state as it evolves over time. We get, for each measurement, we get a measurement. You can see how noisy those are. For each of those measurements, though, at each point in time, we get a predicted mean, which are the stars, and then we get this correction to it. And that gives us an idea of what we're going to do. So before we get to the full equations, if we want to do an n dimensions, what happens if the state vector is more than one dimension? Well, all these things become matrices. So I have a prediction phase and a correction phase. So I have my D matrix, my M matrix, and my covariance matrices. I can use those to correct. Given a measurement, I can make a prediction, do the correction, and I can iterate this loop. Now it is worth noting that this common matrix that comes out of this is called a common weight matrix. When it's small, we have less weight on the residuals as the covariance matrix approaches 0. So if it's small, we put less weight on the measurements. And if it's larger, we put more weight on the measurements because we say the measurement errors go to 0. And that's, you can see that because this term here is taking an inverse. So when this is very small, this is going to become dominated and k will become smaller. Okay. So coming back to that simple model with just 2D position, no velocity, no estimate, we assume that where we saw something is where it's going to be. We have some initial position, but we have some uncertainty, so we have some prediction. We see a measurement of where it is the next time frame, and we update our model, and this will continue. We can represent all these in terms of matrices and their noise processes. I don't expect you to actually implement these, but I thought it would be good to go all the way through and show you a full model example using existing code for a common filter, say from OpenCV in this case. So coming back to our 2D constant velocity model, we have our motion equations for our matrix D, our measurement matrix, and we're just going to assume very simple process noise model. So we're going to assume our process noise is a constant of 0.001 times I. So assuming there is no covariance, they're all independent. We're going to assume our measurement noise is equally independent. We have independent noises of 0.1 for x and y. And our initial error covariance is going to be 0.1 times I. So very, very simple models, but you'll see how interestingly well this works. So the problem we want to look at here is a very simple tracking problem. We want to track what's the position of a mouse and make a nice smooth prediction of where the mouse is going to be next. You can imagine this for the mouse because it's easy to interact with a mouse. But you can imagine this for any other 2D position variable, for example, in one of your games. To do this, we're going to use the OpenCV libraries just to show you a different set. There are libraries for this for MATLAB and lots of other packages. I just thought I'd show you something different. OpenCV is a library for computer vision. It's pretty easy to use for lots of these basic operations. So it has a class called the Kalman filter. It's going to take care of the equations for us. We're going to give it a time sample here of 1. We're going to define our transition matrix of 1, 0, t 0, 0, 1, 0, t. And just go back, right? We're going to pull that out of this. Our state vector is x, y, x dot, y dot. So the first equation is 1 times x plus t times x dot. So we get the 1, 0, t 0. Similarly, our second equation, 0, 1, 0, t. And then our last equations for x dot and y dot are just 0, 0, 1, 0, 0, 0, 0, 1. That's actually the hard part of setting it up. You have to think of your model for what your variables mean. You're going to have to tie those back to what we're going to do. Our measurement matrix is 2 by 1. Although I drew it here as 4, we're just going to project away 2 of the dimensions. So we're going to set our measurements to the x position and y position of the mouse. We don't get any other measurements. So that sets up our measurement matrix. Our covariance process noise is 1 e to the minus 4.001 times the identity matrix, the measurement covariance similarly, and the post covariance just based on those last numbers. You could do a better job with modeling what those errors might be, but we're not going to get into that for this. For the mouse, it's pretty straightforward. So now we've set that up to show you an example of how simple it is to use a Kalman filter in OpenCV. We basically build a matrix called a prediction, where we call take the Kalman filter, make it do a prediction. We can then take that prediction object and get its position for x and y, 0 and 1. So we're going to get a predicted point. We're now going to go sample through the computer, getting the mouse's information for x and y. That gives us a measurement point. And then our correct phase is going to take that measurement, okay, and take our measurement from up here we got from the mouse, update that, give us an estimated, and then we can have a point that is the estimated at positions. And you'll see that as we go look in the video. So before I show the video, the red point X here is the measured point. The greenish X is the predicted state. And then the blue line shows the raw measurement history. The green line shows the state history as those two progress. It's the video. So again, red point is the measurement of the mouse. The green point is the estimated state. You'll see when they're moving smoothly, the Kalman filter does a good job. But now it's just the mouse starts to get erratic. You can see the predicted state still does a nice job of smoothly following it. You can see where this might be useful if you're trying to estimate a smooth curve as someone's doing a drawing and you don't want to have all the jitter in it. Could also be estimating positions of players in a game or something else. So anyhow, that was a nice brief introduction to Kalman filters. There's a lot of linear algebra that goes into them, the basic equations. These are based on slides I got from some faculty at UCIC, Austin, Stanford, and Australian National University, and a couple other references if you want to see them. The last two, Bishop and Welch, says the math worked out in more detail, and the OpenCV example for what we saw there at the end.